Okay, thank you very much for inviting me. It's a great pleasure to join in this meeting. What I'm showing you on the board at the moment is effectively what was my life until recently. So what I've worked on most of my life is sort of very basic motor control. So we worry about things like feedback, how you generate motor commands, a function of the state, the position, and the velocity of the hand. And we worry about how you estimate, say, Bayesian estimation. And we worry about motor noise and how you plan and the consequence of motor noise. We also worry about learning, how you learn parameters of the system, or how you learn structures of the world. But recently I was convinced there's a little bit more to life than motor control. So I want to tell you about a sort of new area of my research, which brings in something from above, and that is decisions. So I was lucky to have Michael Stadman visit my lab on a year sabbatical. He doesn't care at all about how you make movements, he just cares about the decision you're going to make. Whereas my life, I only cared about what movement you're going to give. And as long as we tell subjects what to do, I don't care what decisions they make. But he convinced me that actually there's a lot of similarity between decision-making and motor control. So decision-making tends to be about complex stimuli, so complex in environments where you have to make a simple binary choice, left, right with the eye, ideally. Whereas motor control is all about simple stimuli, gives them a target to point at, but about complex control problems. And these fields really live in separate silos. There are completely different formalisms for them, there are different conferences for them, so there's very little talking between the decision-making community and the control community. And that's surprising because actually decision-making and motor control rely on very similar mathematics. So they both rely on streams of noisy evidence or commands, and they rely on inference, time constraints, and costs. So the goal of what we've been doing together is really to try to break down this barrier and look at the interactions between decision-making and motor control. And what I'm going to tell you about today is our sort of initial forays into looking at how we can link decision-making and motor control formalisms in a common framework. And I'm going to go through four things today. I'm going to go through about decision-making and control in terms of confidence, choice, and action, and multi-stage decisions, two recent studies. I'll then move on to what the motor system knows about the decision-making system in terms of reflexes and decision variables. And then I'll probably finish on active sensing. The idea is how can you use the motor system to extract things to make efficient decisions. And if there's time, which I doubt there will be, I'll talk about some recent work on multiple decisions and plans. So here's a typical problem. You're in a lovely English forest, and you have to make a binary decision whether to go down this path or this path. And what you'll notice in English forests is something very common, that this part over here is very worn down. And there's a good reason for that. What people tend to do is head off down one direction and change their mind. And so one question we can ask is, why do people change their mind having committed to initial decision? And that's one question we want to address. But what we know about the initial decision is decisions in general take time. You have to, for example, maybe extract information from the environment, which takes time, or maybe you have to extract information from your own memory. So it takes time to make a decision, but finally you'll make a decision. Maybe in this case you'll make a leftward decision. But associated with that decision may be a level of confidence. How confident you are that that's the correct decision to make, depending on what task you want to achieve. Maybe you're looking for a lost colleague, or looking for the most beautiful route to take. You can then head off, having made that decision, use your motor system to project you down that path. But you can gather more information then, or you could reconsider the information you've already got, and that may well change your confidence. And it could even lead you to revising your initial decision to change your decision. And so what I want to tell you about now is sort of a modeling framework and experiment to ask, can we unify these five things? The time to make a decision, your initial confidences, changes of confidence, and change of decision, all within one package. And to do that, we're going to do a very simple psychophysical task. We're going to ask people to make a four-choice decision. So they start with their hand at the center here, and there are four possible choice targets. And what we do is we project down into the plane of movement a random dot kinematogram. Now, my first three experiments are all going to use this, so it's important to understand this task. On any given trial, most of the dots are either going to the right or to the left. So your job is to decide, are they going right or the left? As a subject, you're told, just look at them and tell us the net direction of motion, is it right or left? And the way the stimulus is constructed is on any trial, a proportion of the dots in any frame actually are shifted to the right, or in other trials to the left, and the rest are replaced randomly. So this is a very easy trial. This is where 50% of the dots are translated on a frame, whereas the rest are being replaced. So it's very easy. You should all see it going to the right. If you don't see it going to the right, you should see a neurologist. There's something wrong with you. We can make this task very hard. We can make 1% of the dots move to the left. And it's a very hard task there. So we can titrate the difficulty of this task. And the nice thing about this task, it requires you to accumulate evidence over time, and it sort of slows down the normal decision-making process so we can then study it in the lab. So your job is to decide is it right or left, and you'll indicate that by moving to the left targets for leftward motion and the right targets for rightward motion. But we also want you to tell us about your confidence in that decision. And so we tell you that if you're highly confident, you should move to these targets. If you have low confidence, to these, and we actually alternate those in blocks to make sure it doesn't really matter whether they're top or bottom. And the way we encourage people to report the correct answer, or their correct confidence, or a real value of their confidence, is they get more points. Points mean prizes. They get more points if they get to these targets and are correct, but they'll lose lots if they're wrong. Whereas they get fewer points for these, but they lose fewer as well. So we encourage them to report their confidence reasonably rationally. So critically on any trial, they have as much time as they want to make the decision. It's a reaction time task. So they look at the dots. When they've decided to make a decision, they start that movement, and the moment they start the movement, we turn the dots off. So the dots are only on before they initiate their decision. So off they go and they make a decision. Now, because I'm working with Michael Shadden, who's a primate neurophysiologist, we run this like a monkey experiment. We have 3 subjects, but we run them over 3 weeks to get something like 15 or 1,000 trials. Okay? So we're looking at small numbers of people, but large numbers of trials of highly trained people. And so here are just some trials from one subject. And what you'll see is most trials go straight to one of the targets. Here, there's a high confident leftward decision. But there are about 5% of trials, subjects head off towards one target and change their mind mid-movement, even though the dots have gone off. So here they were going to a right high confidence, but they become low confident during the movement. And then about 3% of trials, we see people change their decision. So here, oops, sorry. Here they were going to a right high confidence target, a right low confidence target, and they changed their mind to go to a left low confidence target. So I'm going to present a model now, which is a well-known model to explain the initial decisions, but then I'll extend it to explain these changes of decision. So the model is for sequential sampling. The idea is at each moment in time you extract some evidence from these dots for left versus right. And the way you do that is you have detectors in your brain which detect motion, and here you have a detector for right versus left motion. And the idea is, because there really is a rightward motion, this is going to extract positive evidence, positive numbers, from a Gaussian. Now the reason it's a Gaussian is there's noise in the stimulus and there's noise in your brain. So we assume you're extracting the evidence on average with positive numbers because it is rightward, but there's some noise. The leftward detector effectively is going to extract basically evidence against leftward because it's really rightward motion in this trial, and again there's noise. And the noise in these two is actually correlated because some of this noise comes from the stimulus and some comes from the brain. So we expect the noise to be anti-correlated effectively in terms of the evidence. And the idea is we'll set a race here. This one's going to race up to some amount of evidence which will make a decision for rightward. This one's going to race to this decision bound for leftward. And we set the race off. So we're doing basically a drift diffusion type model. And off they go. And on this particular trial, the rightward got there first, so you make a rightward response. But because of noise in the system, the leftward could have got there and you could have made an incorrect response. And I can plot these on the same graph to make it a bit easier. And what you can see is the decision is very easily formed then. Then the movement starts some sort of roughly fixed time after this, because it takes you time to start your movement off. But how do we get confidence out of this model? Well, confidence falls rather nicely out of this model, because although the winning race is always at the bound, so there's not much information there, the losing race tells you something about how confident you've been. Had the losing race been almost at the bound, you shouldn't be very confident, because the losing race could have almost won. If the losing race is very far from the bound, you should be highly confident. So it turns out you can use where the winning and losing race are, as well as the elapsed time, to map that into the log odds of a rightward versus leftward choice. So this is our sort of metric of confidence, your belief that the rightward choice was a correct choice when you made it. And so I'm putting that down here. Here's the log odds of a rightward choice, taking this data, transforming it, and so generally in the right half of space, and you made your decision there. And since we're asking for a binary decision in our task, are you high or low confidence, a natural thing to do is put a flat confidence bound on here. If you're above this confidence bound, you'll be highly confident, and below it, you're low confidence. Yes. How do you get this from this? With this, you get this effectively by asking what's the probability of being in this state had it been a rightward choice or a leftward choice. So you have the generative model of how the state is generated. Okay? And then you can basically say, right now, given the levels of coherence I've got, what's the probability if I have this one here, this time, that it would have been a rightward diffusion process versus a leftward diffusion process. Right, coherence. Whether the dots are really moving to the right or left. So it's a simple calculation. No, I'm not convincing you it's simple. So you can say, if it had been one of my positive dot motions, how probable would it be I would have at least two states at this time, and if it was leftward, how probable would it be? Those are easy to calculate.
But I thought, so you're not getting it from a single trial?
Yes, from that single trial, you can take these three numbers, effectively, the time and these two values here, and from that trial you can map that into the probability that it would have been rightward motion.
Like first passage time probability?
We don't even have to do it. It's even simpler than that, to be honest. You can just work out the probability that I would be at these locations independent of the bound, given a diffusion process with this covariance, these means. It's a simple calculation. Okay. So we can get this, and we split it. So we've got four parameters in this model. We've got a parameter which links the strength of the evidence to this mean. We've got a parameter which tells us the height of the bound, and we actually have a flat bound in the model. And there's another parameter which says how long it will take us to move, having hit this bound, and a fourth parameter, which is this one here. And so with those four parameters, we can do a reasonably good job of modeling the initial decisions. We fit them. So this is motion strength. This is from very difficult to very easy, and this is the probability of being correct. And clearly, the easier the task, the higher the probability of being correct. And if you split them by what we call high or low confidence, we get a nice split. If you're highly confident, you're more accurate. If you're less confident, you're less accurate. And we can use the same model to predict how long it will take to make a decision, shown here. Here's the time it takes you to start the movement. The easier the task, the faster you are. But interestingly, the more confident you are, the earlier you will have moved in general. And that's because moving early is a sort of metric that you have good evidence, and therefore you should be highly confident you hit the bound quite early. And we can see that for all our subjects, so we can account for four subjects here. We can account for the data for reaction time and accuracy. But our real interest is in the changes of decision. Why, even though the dots have gone off, do people change their decision in this task? And if you think about it, the stimulus comes on at some point, and it's going to go off when they start moving. But we know from common sense and neurophysiology that there's a time delay between the stimulus going on and you beginning to accumulate evidence. It takes time to visually process the information and get your motion sensors going. And so there's a sensory delay here. More than that, from hitting this bound here to actually start the movement, there's a motor delay. And so what this means is whenever you make a decision, not just in our task here, but whenever you choose to make a decision and start a movement, there's a period of time you can't use of the sensory evidence to make that decision. And this time is long, it's about 400 milliseconds or so. So whenever I choose to move my eyes or my arms, there's extra information in the processing pipeline that I could still process even though I've started my movement. And the real question of this study is, do you process information? If so, how? So a natural thing to think is that maybe even though you started your movement, you carry on processing this part of the non-decision time, as we call it, evidence. And the natural thing then to do is to ask what happens. You have a highly confident in this particular trial, but now they have come together, you may well change your confidence. And so what we can do here is we could just propagate our bounds, high confidence, low confidence, leftward decision, rightward decision. If you did that, you would have many, many, many changes of decision and changes of confidence. So we don't do that because effectively we believe there's a cost to changing a decision. There's a physical cost of effort. If I have to move to one target and then correct to the other, it requires more effort. So a natural thing to do is to add some hysteresis in, and we move all the bounds away from the initial decision. So we have three extra parameters. We fix the other ones from the initial decision. And with the three extra parameters, we can explain the patterns of changes of both confidence and decision we see in our subjects. And even though the patterns are slightly idiosyncratic among our subjects, just through the three parameters, we can capture them. So for example, here is motion strength. And the blue is the probability of changing confidence, which is always higher than the probability of changing your decision. And that's not surprising, because if you're highly confident, you have to go very far to low, which you have to go much further to a change of decision. And we see that effectively, we see idiosyncratic patterns well captured. And in fact, we can capture quite nicely the conditional probability of changing confidence or changing decisions. So this is a probability of correcting an error as a function of motion strength. If you're at high motion strength, easy task, you make an error, you're almost always going to correct it. Whereas the probability of spoiling a good start is quite high for low motion strength. And this is the same data from going from low to high to low. So we think the sequential sampling framework can unify decision speed, accuracy, and confidence, as well as changes of confidence and changes of decision. So within the sort of field of decision-making and confidence, people often argue that confidence and decisions are separate processes. And effectively, confidence doesn't have to agree with decisions. But most of those experiments, almost all of them, require you to report confidence after you made a decision. So a typical rat experiment would be the rat makes a decision and they'll look at how long the rat will wait for a reward as a measure of its confidence. What our study shows is if you measure confidence and decision at different times, they'll have used different amounts of evidence. It's only by measuring at the same time that you get this effect. If we measured confidence later, because of changes of confidence, we get a dissociation between the two. So we think that this is a nice model to start with understanding how we have confidence and decisions interact. But I made it sound like everything in life is a single binary decision. That's, yes?
You showed that you can be starting from correct decisions, and you can be designed for changing. But what about the incorrect time? Because that's usually where these kind of models fail.
What about the
incorrect trials and fitting for the time of these? Because usually this is where these kind of models fail.
Fitting for the time. So what I showed you here is the probability of changing from correct to incorrect. You want to know the time of making an incorrect decision?
I want the ones that were just simply incorrect.
And you want to know what the initial time?
The time, the response time.
Or the response time. So those models you can do if you don't use a flat bound. You need to use a collapsing bound to get the incorrect ones fit well. Okay. So here we're using flat bounds. Actually, one of the tricks there is we don't fit the incorrect reaction times when you're doing flat bounds. In order to get this accurately, you have to fit a collapsing bound model, and then you can get the incorrect ones very well fit. But we've shown we don't bias our results by only fitting the correct reaction times in particular. Okay, so the world isn't really like this. Here's what the world is really much more like. The world is like you have to make many decisions in a row to achieve some goal. And most of the time, you never know whether you're right or wrong. Okay, and it's only in very few circumstances when you make a bunch of decisions, you know you're right or wrong. When you make a bunch of decisions to decide who to marry, you've no idea ever whether you're really right or wrong and there are better decisions. And so, one question I want to ask is, if you're going to make a sequence of decisions towards a goal, how does one decision affect the next decision in the series, and so on? So we're going to look at the simplest version of this, where we're going to ask people to make 2 decisions in a row, but they've got to get them both right for a reward. So effectively, there are 4 choice targets here, 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 and only one of them is correct. And they're going to make 2 decisions in a row using eye movement. So we're going to show them a random dot, they can look at it as long as they want, and then they make a decision by moving their eye to a choice target. So they move their eye here. When they get there, we then give them a second random dot, up or down, and they make a second decision, and then we tell them whether they're right or wrong. But they have to get both right to be correct. And importantly, the difficulty of these 2 tasks are independent. So you can have easy, 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 hard, hard, easy, hard, hard, and all other varieties. Okay. So first of all, we can account very easily for the first decision, not surprisingly. The first decision is a sort of a decision in isolation. So here we can fit our very simple drift diffusion model, probability correct as a function of difficulty or easiness, and here's the reaction time. Not surprising. What we're much more interested in is what happens on the second decision. So if we look at the second decision, and we split the second decision by what happened on the first decision, we see quite big differences. So we're splitting the second decision now, whether the first decision was a correct decision or an error decision. So if the first decision was correct, you tend to take much longer on the second decision than if it was an error. And more than that, you tend to be more accurate on the second decision than if it was an error. Now, you could argue, maybe this is just co-fluctuation. Maybe attention fluctuates trial to trial, so when you're more accurate on the first, you'll be more accurate on the second. And I think we can rule that out in a number of ways. And one way we can rule that out is to say, what happens if I just ask you to make a second decision? No first decision, I give you that for free. You just have to make the second decision now, this vertical one, to get your point. Well, then you're even slower. Okay? So now you're much slower and you're more accurate. So fluctuations can't explain why that would be higher. If it was just fluctuations, you'd expect that to be somewhere in the middle between the 2.
Even the slow one in the second one is slower than the first decision, right?
Say that again?
So I'm saying in the slow decision in the second one, it's slower than the first decision.
Yes, that's correct. It is slower. Yes, that's a fact.
So I'm saying it's like when you're having only this one, it's only one decision, it's about the same as the first one. So the more decision you make, you get it faster.
there's complexity in that there's a horizontal versus vertical eye movements. They don't have the same processing or the same non-decision times to plan those movements. So we can come back to that if you think it's important when I finish. I don't think it's important. Okay, so that's one reason we don't think it's fluctuations, but probably the most stronger evidence of not just co-fluctuations is that if we just plot the reaction time on the second decision as a function of just the difficulty of the first decision, there's a strong effect. The easier the first decision, the longer you take. And that can't be affected by fluctuations. This is just difficulty. It's got nothing to do with fluctuation. So there's something coming from the first decision to the second decision. Okay? And why might that be a good idea? Well, if you think about it, it makes sense that you might want to change what you do on the second decision based on the first. So here is my expected reward overall, my probability of making my 1 point, based on how long I'm willing to integrate evidence on the second decision. If I come in highly confident, and I just make a decision instantly, I'll be 50-50 right on that second decision, and that's my reward. But if I integrate more evidence, I'll increase my probability of being correct overall. It'll never go to 1, because I could have made a mistake in my first decision, and I can't recover from that. However, if I come in with low confidence, I'm going to start at a lower level here and plateau at a lower level, because I can't recover if I probably made an error on my first. If we believe there's any cost on time, that time costs you in this, so maybe there's a cost of time, then adding those together will give you some optimal sort of amount of time to integrate them. And if you're highly confident, you should integrate for longer because the chance of getting a reward are better. And in fact, when we just do a single second decision, it's like going into a decision where you've been 100% confident you're right, therefore you should take the longest amount of time to get to your point. So the idea is you've got this sort of drift diffusion model going here. What do you propagate from the first to second decision? Well, we don't think you can propagate performance because you don't know performance. You don't know whether you're right or wrong. The only measure you've got really is confidence. So our assumption is you're going to propagate confidence, although we do test other models such as just difficulty, but don't think so well. So you're going to propagate confidence, and the question is, what is confidence can change in the second decision? It could make you more attentive. You could improve your signal to noise. You could decide to change the bound heights. And so we're going to look at a variety of models to ask that. But before we do that, we need to get a measure of confidence to know what the confidence is likely to be after your first decision. And the way we get that, we have in other trials where subjects make the first decision, but we stop the trial there. Okay? And then we ask them, can you report on a scale of 0 to 1 how confident you are you made that first decision correct? And we both do trials where they don't know it's going to report, as well as ones where they know it's going to get a single decision, and we get very similar ratings on both. So here's the ratings. Here's confidence on the scale of 0 to 1. Here's how long it took them to make a decision. What we see is what we expect to see based on previous literature. The easier the task, the higher the confidence. The longer they integrate it for means the lower the confidence, means they think it was a harder task. And if they make an error, which are these thin lines here, they're less confident as well. Okay. So we can use this data set to basically do a k-nearest neighbours to predict on our double decision trials how confident we think they would have been given the coherence we gave them as a difficulty, how long it took them, whether they were correct or not. So we're going to take that and ask, what does that affect in the second decision? And we're going to compare a bunch of models, and I'm going to tell you the winning model is the following. The winning model says the bound on the second height is some constant, plus a linear increase in the bound as a function of the confidence. Okay? So the more confident you are, the higher you're going to set those bounds. And so I can show you on these three subjects. Here is the estimated confidence, and here's where we think you put your bound from the model. And the dotted dashed line is actually the best model, which is it linearly increases. And to show you I'm not really cheating, I can instead break our confidence down to 5 quintiles and fit each quintile separately, and it's approximately linear over the range. So this suggests that effectively confidence is a very important feature for setting the next decision. When you go through multi-stage decisions, or at least 2, you use your confidence to set parameters on the fly for the next decision. And it gives a degree of flexibility. You can rapidly and precisely change on a trial-by-trial basis, effectively, your decision bound. This, we can show, is roughly optimal. It's definitely rational. The model we're using is not optimal, because we're again using flat bounds, and as we know, people like Alex Boucher have shown you need to have collapsing bounds for optimal in this task. It turns out it was too hard for us to fit with collapsing bounds for this, but we expect this is probably quite close to optimal behavior, perhaps to get the most reward. So up till now, I've really said that we have good models to explain this precision changes of mind, but I made it sound like you hit this bound, and then the motion gets called into play. You've got the dots going, you hit a bound, the decision variable gets passed down, you get this sort of executive saying, move to the right. And then the motion prepares and happens. sounds like a very sequential set of processes. But there's another possibility, is that somehow the motor system gets to know about features of decision tasks online. And the question I want to ask in this is, does the motor system know about the decision variable as it's being accumulated, or is it only told once it hits a bound? And to do that, we're going to try and relate two important features. We're going to try and relate the decision variable, that's where you are in this sort of Y space here, from the distribution model, with the gains of the motor system from optimal feedback control. So you've heard a bit about optimal control. The way you think about it is when you've got your optimal stochastic controller, you sort of have a feedback controller that tells you how the arm should respond to perturbations, or to basically to generate a movement and response. So we're going to measure on a trial-by-trial basis the reflex gains and the decision variable as best we can and try to relate the two. And the way we do that is, again, subjects sit holding onto a robotic random this time, and they see random dots which are either moving in the elbow's flexion direction or the extension direction. And in this particular experiment, they don't get to choice when to initialize their response. We basically tell them when to respond. And the way we do that is two things happen. The unimportant thing happens is dots go off. That's really not important for this experiment. What's much more important is the robot moves their hand 1 centimeter in 60 milliseconds, a very fast movement. Fast enough that it sets up a nice stretch response. Okay, so it's like doing a knee jerk. So it sets up a nice stretch response, and we can measure that response in the muscles which control the elbow. And then we ask them to tell us their response, and we tell them whether they're right or wrong. So first we look at behavioral data, which is very simple now. It's a one-parameter model to fit this data. Here's viewing duration. Here's the probability of being correct, and we control the duration from very short durations up to long durations for easy to hard trials. So not surprisingly, the longer you integrate, the better you are, and also the easier the task, the better you are. Simple model just says now we just have a one-dimensional diffusion. The mean is proportional to the coherence, and therefore you're going to basically integrate up to a bound, up to some time with no bounds. You just integrate all the evidence, and therefore the decision variable we distributed normally with some k from unknown variable times the coherence, which is these numbers here, times time, and the variance will just be time. And so basically, very simply, we can fit that model to the subjects. We can ask what's probability of them having a rightward versus leftward choice. And if we do that, we can do a reasonably good job of accounting for their data. So we've got a model which can predict now the decision variable in any trial as best we can. So we now use this model on a trial to say, given they've used 400 and they made a rightward decision, propagate my normal distribution, truncate it whether they were positive or negative, and find the mean of that truncated roll. That's my best guess. We also measure the reflexes. So the dots go on, they come off, we perturb them, and we measure in a very short period, in that sort of 150 milliseconds after perturbation, we measure the EMG. And I'm not going to describe how we do it in detail, but effectively we can pull out measures of the reflex gain in favor of the direction they're going to move in the end decision they're going to make. And we measure that over 3 periods here by adding it up effectively. We sum it over these 3 periods. This is the short latency reflex, goes through spinal cord, won't be adaptable on these sorts of time scales. That's like a control, that should be flat whatever happens. These medium and long-term latencies probably go through motor cortex. They're not under sort of individual voluntary control so much, and then we have voluntary movement out here. Okay, so what could happen? We're going to plot our reflex gain against our decision variable from our thousands of trials we do on individual subjects. Well, one possibility is until I tell you to respond, you just don't get the motor system involved. I wait for my perturbation, and then I get my motor system involved, and I respond. Another possibility is I need some amount of evidence before I'll even bother turning my motor system on. Okay? There might be some bound of evidence I have to reach before I get my motor system involved in the process. But what we actually find is that right from the earliest amounts of evidence, the motor system starts tuning its reflexes almost in proportion to the decision variable. So here's the decision variable. This is our monosynaptic reflex spinal cord, nice and flat as we expect. Here's the medium latency, 45 to 75, and we see even in individual subjects a very nice increase. And the long latency, an even nicer increase. And this is our group data. So it suggests that the system is really responsible for this. And if this was really being driven by the diffusion process, we can make a rather nice prediction. That if we believe the decision variable is what's driving it, the decision variable is distributed like this. If we look at our 0% coherence trials, that's trials where the dots are all moving randomly, yet you'll still make a decision, then we know that effectively the distribution of the decision variable will be 0 mean with variance of time. If this linearly increases the decision variable, then the variance on these trials should also linearly increase. And this is a plot of the variance of the reflex gain for 4 subjects as a function of viewing duration, showing that the variance increases as well.
It's not again the experiment.
The experiment? Yeah, okay. The experiment is you look at the dots, And when I give you a cue, basically, I'm looking at the dots. When I give you a cue to move, you have to tell me they're going this way or this way. So we control the duration and difficulty, but we also use the robot to extend the arm at the same time we ask you to report, and that sets up a reflex gain we can measure. So, yeah, so what I'm showing you down here is what we infer their belief is where they are in decision space, based on the difficulty of the task, how long we gave the evidence, and whether they end up making a correct or incorrect response. What I'm measuring here is what you measure from the EMG, the muscle activity, which is a measure of how strong the response is. Okay? And then I'm showing you here, this is just the reflex gain, this is the variance of the reflex gain, which shows it increases rather nicely linearly, which is a prediction of the drift diffusion model. The variance should increase linearly when there's no evidence. And the reason you do this, maybe, is you get to the task, you get to the goal faster. So as a function of the size of the decision variable, you get there quicker if you're at a higher decision variable. So we think there's a continuous flow from decisions to motor systems, and we think this provides evidence that effectively most of them gets involved right from the very earliest stages. Okay, I need to move on. I'm going to cover this one more topic.
This is a conclusion in the end, or is that part of?
No, this is a conclusion, I would say. I would say it's a conclusion that the motor system knows about the decision variable as it's accumulated. Yes. Okay. Finally, I want to take a slightly less motor-centric view, because I've talked about, people think of motor systems achieving tasks of, picking objects up or trying to achieve tasks, but the motor system has another use in that our sensory apparatus is attached to our motor system. And so there's a nice field in machine learning of active sensing. How do I take my data, in the world to best fit my models? And given that our motor system, has our sensors on them, we can ask maybe we're moving often in ways to extract information. So if you look at these two scenes here, there's an animal hidden behind each of these foliages, and it's your job to determine what it is. And to do that, you're going to have to scan between these small patches and accumulate evidence in some sensible way to determine what it is. And it makes a behavioral difference, because you want to know whether it's a cheetah or a zebra behind it. We can easily formalize this task with an Bayesian active sensor. You've made a couple of eye movements, extracted disposable information from here, and therefore, given the evidence from your previous fixations, and a prior over perhaps furs of animals, you can use a nice model of perception to generate your posterior. That might be a cheetah given the evidence, or a zebra given the evidence. And then what you might want to do is decide, if you're not sure which one it is, to extract more information. And what you want to do is determine where you're going to look next to get the best information. And ideally, you find a good location and make your saccade there. Now, there have been quite a few studies of active sensing in sensory motor control and perception, but most of them, or probably all of them, have focused on very simple tasks like finding a hidden object in a cluttered scene. Whereas really what we're interested in is something like abstract information extraction. And so we're going to look at a task where we look at more abstract information, but also one where we can quantify for the first time fixation efficiency, to ask really how efficient you are, which doesn't look at things like geometric patterns of eye movements, but in fact extracts more interesting evidence. So the task we have is very simple. We're going to generate furs. We're going to have patchy furs and stripy furs, either horizontal and vertical. And the way we generate these furs is we generate them with Gaussian processes. So this has got equal length scales, and it's got unequal length scales. And the nice thing about Gaussian processes, we can generate infinite number of examples where no pixel in itself is informative. So effectively you can't just focus on one point. So here are a whole bunch of patchy, here are a whole bunch of stripy, they're all different, but they're all from the same generative model. We first of all train our subjects. We give them the whole patch, we say, is that stripy or furry? This is totally trivial. No one gets anything wrong here. When you can see the patch, it's totally obvious. But we show them these to get used to the statistics of the visual scene. We're then going to go to an experiment where we're going to control very precisely the evidence they're allowed. They start off with a blank screen, effectively. It's actually a black screen. And they can make eye movements. But whatever they fixate, we reveal a small Gaussian patch of the image. And they're allowed to make between 5 and 25 saccades, or fixations. But we as experimenters control that. They don't know on any one trial how many they'll be allowed to make, which enforces them to be somewhat greedy in getting their evidence. They make modeling tasks easier. Okay? So they make up 525. When we finish, we basically say to them, patchy or stripy, they give a response, and we tell them whether they're right. And then we have other trials where effectively we passively reveal the patches. Okay? So now we reveal them one at a time to the subjects in some pattern, and again we ask for a decision. Importantly, in this particular experiment, at the end when they're all revealed, we let them rescan as much as they want, so they can absorb all the information they've got to get that information, so we can equalize the information between these two. But we've done controls to show that effectively this, which is our critical one, it doesn't matter whether you rescan or not, you get the same basic behavior. performance. Here is the probability being correct as a function of how many we reveal when you're allowed to actively scan and render. So the more saccades you have, or fixations, the better you do. And what the blue shows is what happens if we just reveal a Gaussian isotropic location. You do really rather poorly. So clearly, choosing your own revealings is better than us choosing random revealings. And we can account for that behavior with a very simple observer model, which says we have a 4-parameter observer model. We will allow for biases in the length scales. People may not have completely got the correct length scales. We allow 1 parameter to account for biases. We have 1 parameter to allow for perceptual noise. When you see a pixel or patch, you may not be able to get the color quite right. We add just Gaussian noise to that. And we have 2 parameters of decision noise. We have a lapse rate, and we have some noise effectively determining what's the best category. And using that, we can do a reasonably good job of accounting for the individual performance and the group. We can use that model to say now, how informative are the regions we reveal? And what we show is when we reveal random ones, they're much less informative in general, in terms of entropy and bits, than if they free scan. Okay, what about the actual scan patterns? Are they really doing something active in this case? Well, this shows our 3 subjects. This shows the average location of the 2-dimensional scene where they scan. And people tend to like to stay at the middle. There's some idiosyncrasies, so we don't really focus on these averages so much. What we focus on the difference from the average of when they have either a patchy thing underlying it or a horizontal strike or vertical. And their job is to report to striking versus vertical. They don't have to detect the horizontal or vertical. What you can see is that the patterns are somewhat different between these things, suggesting as they're revealing evidence, they're changing their scan patterns. And the way we can show that, effectively looking at the average, we can basically say how correlated on different trials, for example, are the scan paths within a category, and we look at those, they're positively correlated, and they increase as you get more scans, compared to comparing them across different underlying images where they're negatively correlated. So this is evidence that they're doing something active. It doesn't mean they're optimal in any sense, but they're certainly using the evidence they get to change the way they scan. So we can develop a Bayesian active sensor model in which we probe positions here. This is position x1 in the 2-dimensional plane, effectively, and we get a pixel value, this red blue value. And so after d saccades, or t saccades, we've got d pairs of these. And it's simple given the generative model, which is this Gaussian process, to work out the posterior probability of the different categories, strikes versus patchy, given that data. But then we can ask, what if I went to a different probe location and I saw a different possible pixel? How might I update my beliefs about the categories? Well, trying to predict what I might see here is going to depend both on what category I think I'm in, i.e. stripy or patchy, and it's also going to depend on the data set I've got, because a particular Gaussian process will have some sort of phase information, for example, so you need to know the previous data. And then I can say, well, if I were to go to X star and I saw Z star, here's my updated posterior probability. And so what I really want to do is I want to start with some entropy here over this probability. Now, obviously, we would like to be as small as possible. And I can ask, what's my likely entropy having gone to that location? So what I need to calculate is the average entropy given my belief about what I'm going to see there if I go to X. So I calculate this for a location, and what I want to do is make this difference as big as possible. I want to reduce my entropy. And so we can get this score for every place in the C, and that will tell me how good it is to go to different locations. Now, it turns out this formulation works fine, but you can mathematically write it in a different form. This has got the category on the left of both of these, but it turns out you can write this in a much more elegant and intuitive form, which is the pixel on the left-hand side. So what this says, given that I want this number to be big, I want this to be very big, which means I want to be overall uncertain about what pixel I'm going to get. Okay, I want to go somewhere where I don't know what the pixel is going to be. Now, if I just did that, I would just go as far away as possible from the scene on every trial usually. So what this says is, I want to go somewhere I don't know the pixel, but I want to go somewhere where each hypothesis is very certain what pixel is going to be. They make different predictions, effectively. Okay? So I want to be uncertain, but I want each hypothesis to be certain, and that's going to be most informative. And so the way this works is shown here. Here's an underlying image. Here, after my first fixation, is my BAS scores over the map. And as you can see, the circle is where I make my eye movement. The X, which I can't see here, is the optimal. Now, they can be in quite different locations on this because there are many places which are equally good. So what I'm showing you down here is the percentage value of how good I am in terms of the rank for what I choose compared to the optimal. And as you move on, the map updates itself and I can choose to make different movements. And we can ask, over all the eye movements or fixations you make, Where am I in scores, the probability density, and in general, I'm in the high scores of what's good. But we can now look at the actual predictions of that BAS map, the BAS algorithm. And here are the predictions of the optimal distributions of things to do with your eyes, if you want to go to the optimal location. And now we can compare, for example, how the subject's behavior are performed across within a category against a cross category. And what we see is, again, a very strong positive correlation with the optimal algorithm. And a negative one, if you compare what people do under Stripey with what they do under Patchy, for example, from the algorithm to the subject. So, we've now got an algorithm which knows optimal. Could subjects have done better than this free scan? Well, we now can predict what the best locations to go is. And imagine we've given those locations passively. So now we're going to reveal to them what the BAS algorithm says is best. Could they do better? And the answer is yes, they can do substantially better. So by revealing the optimal locations, they perform substantially better than if we just let them choose the locations themselves. And the final question I'm going to ask is, what can bridge this gap? Why are they suboptimal? Is it that they don't have an ability to select the optimal locations? Or is it other active sensing components which are corrupting their ability? And it turns out we have to incorporate a few imperfections into the system to be able to account for this gap. So one imperfection is, in the non-ideal BAS, is subjects have an inaccurate prior. And so we model that with one parameter I told you, we fit that to their choice data. We also know they have perceptual noise, which you have to include into the BAS model. So they have to have perceptual noise and their accurate prior. And more than that, even if they know where they want to go, we know saccades are not perfect. So we actually measure in a separate experiment the motor noise. We measure the motor variability and biases. We don't fit them, we measure them from data. And we use these three things to predict how well could BAS do if it was corrupted by the same things that the subject had. And the answer is, it reduces performance. It doesn't bring it to the same as the subject, there's still a gap, but it brings it pretty close. In fact, subjects are almost 70% efficient in this task. And finally, just people say, well, what about heuristics? Surely you know all heuristics. I'm not going to go through this. We've compared three very intuitive heuristics, and they don't do anywhere near as well as the optimal others with the subject's performance. So we think it's hard to come up with a heuristic, it's hard to come up with an infinite number of heuristics, but this one heuristic doesn't work. So active sensing for decisions, people are 70% efficient, and I think by not looking at the geometric pattern, looking at the information that we'll get, we can measure this much better than has been done in previous active sensing. Let me just summarize and ask a question.
Can I ask a question?
Let me just summarize, and I've only got one line to summarize and ask a question. So, I hope I've made through decision-making and control to interact somewhat. I've shown you that there's a one-way from decision-making to control. We have other experiments that show that actions are going to do can affect the way you actually make decisions in the first place. So I think there's a bidirectional, interesting interaction. I think confidence is a really vital part, because that's all you ever know about any decision you make. Motor planning decisions, we see that reflexes track the decisions. And finally, the active sensing decisions important, about 70% efficiency. Just to point out that experiment, as you saw, was done with Matthew Langdell, who's here, who's happy to answer any technical questions on that. Just finally to say, when you see animals doing simple sensorimotor tasks, just remember the complexity of what's really going on inside their brains. Thank you very much.